Hey everybody, Dr. A here, and in this video we're going to be exploring another buckling example. So let's go ahead and get into it. In the given information, we're being asked to compute the maximum force P that the truss can support so that member EF does not buckle. And we're being given the modulus of elasticity of the truss member is 29,000 KSI. Okay, so let's take a look at this truss here. A very typical looking truss, one that we may have analyzed in a previous course like statics. So here we have a roller at A and an external hinge at D. And if we remember, trusses are made of all pin-connected members. So each of these joints is a pin connection, okay? And we have these two forces at joint B and joint C that have a magnitude of P, and that's ultimately what we're trying to find is that magnitude P. And we see that the truss has 3 bays, each one is 10 feet long, and the height is 8 feet tall. Now, member EF cross-section is a solid rectangle that has a 1-inch by 3-inch dimension, okay? And so the idea behind this is when this truss is loaded with these forces P and P, this thing is going to deform, right? So generally, you're going to develop tension in the bottom chord and compression in the top chord, okay? Because this truss is going to tend to want to deform kind of like this, something like this. This is exaggerated, obviously, but you're going to have this thing kind of bend or flex and create kind of a concave up shape, a smiley face shape. But remember, we don't consider moment transferrings between the members because these are pin-connected members, or we sometimes call them two-force members. So all of those internal loads are going to translate through the truss as axial loads, or loads along the axis of the member. So for example, this top chord will be in compression, whereas these bottom chord members, like I said a few minutes ago, are all going to be in tension, okay? And then there would, we would need to investigate a little bit more specifically to figure out what these diagonals are going to end up being. But what we're really just interested in is this EF, okay? So a lot of this, what I just said, is just to kind of refresh your memory on truss behavior. So another thing to note about this is the symmetry. Notice that this truss is very symmetrical in both geometry and loading, which will make our lives a little bit easier. Just by looking at it, you say it out loud to yourself. What are the external reactions here? Well, if you look at this symmetric loading, this external reaction will be P, and dy will also have a magnitude of P, and dx will be 0. So we can clearly see that. Now, if we want to get the force in member EF, what method from truss analysis should we use? Well, if you remember from your knowledge of statics, we have 2 methods we could use. One is called method of joints. The other is called method of sections. We're going to use method of sections. Method of sections works a lot better whenever we want to find out a member force in the middle of a truss system, okay? So I'm going to flip the page here. And before we actually do method of sections, I'm just going to remind ourselves, this is a buckling problem. So I'm going to remind ourselves of our Euler critical buckling formula. That's P critical is pi squared EI over the quantity KL squared. Now, what's the other form of this? Well, we could write this as pi squared EA over the quantity KL over radius of gyration squared, and we can use either version of this. I'm going to use the first version with the moment of inertia term here. Now, what about the moment of inertia specifically are we interested in? Well, that member that we're interested in, EF, has a cross-section that's rectangular. It's got a 3 by 1 inch rectangular cross-section, okay? And so if I were to sketch that out, again, here's this rectangular cross-section. And, here's 3 inches and this is 1 inch. Now, you have 2 cross-section axes here, right? You've got the YY axis and the X axis, all right? And so that means you have 2 cross-section moment of inertias, right? You have IX which will be BH cubed over 12. That's the formula for moment of inertia of a rectangle. And then you've got IY, which is HB cubed over 12. All right. Now, remember, whenever we're calculating P critical, from what we know so far, we need to look at a minimum moment of inertia value. So I'm going to put a little subscript here, I min. Or if we were using the second formula, we would use a minimum radius of gyration, okay? So let's go ahead and punch through both of these moment of inertia values to find out which one is the smaller of the two. So if I want to calculate IX, I say BH cubed over 12. That's 1 inch times 3 inches cubed over 12, okay? And so 3 cubed is 27 divided by 12. This is 2.25 inches to the fourth. Now, IY is going to be HB cubed over 12. So that's 3 inches is the height. B is the base. That's 1 inch cubed over 12. And so this comes out to be whatever 3 over 12 is. That's 0.25 inches to the fourth. So that means that we're going to need to use IY. That's the minimum, okay? So we're going to say I minimum is going to be equal to IY, which is going to be 0.25 inches to the fourth. That means that buckling will tend to occur about the Y centroidal axis. So we'll make a note here. Buckling will occur about the centroidal y-axis, okay? So that means that if buckling were to occur in the system, then this member here, EF, is going to bow out. It could bow down like this, or could bow up like this, or it could bow in and out of the screen. We sometimes call that in and out of plane. But regardless how it bows, it's going to bow about this centroidal y-axis. It's going to tend to warp or curve around this centroidal y-axis, okay? So that's what that means. So we've got the I under control. E is given to us, okay? E was the 29,000 KSI. What about K? K is the effective length factor. K is equal to 1.0 for the pin case. And remember, how do I know it's a pin case? Well, it's a truss, and trusses are made of all pin-connected members. Now, what about the length L? Well, L is just the length of member EF, which is this 10 feet right here, okay? And we're going to have to do some unit management eventually as well. So what do I do? Well, in order to investigate the buckling potential of member EF, what I'm going to do is I'm going to solve for the force in EF using, I said this a few minutes ago, method of sections, and set this equal to P critical and solve for that unknown applied force regular P. Okay, so let's go ahead and draw a free body diagram of this truss. All right, so I'm going to try to redraw this nicely free body diagram of the truss. And this is a good little review of our statics knowledge. Okay, this is a free body diagram of the entire truss. Make sure I drew that like I should have, okay? And then I have P hanging out here, P hanging out here. I've got an AY here. I believe we had a DY and a DX here. And clearly, and let's go ahead and put some dimensions on here, 10 feet, 10 feet, 10 feet. And then, you know, the height, if I put that height dimension line here, we said that was 8 feet, right? So clearly by symmetry, AY equals DY equals P. And we said that earlier. And P, is going to be reacting upwards. Now what we're going to do is say free body diagram using method of sections. And remember, for trusses, method of sections, what we do is we pass a cut section through several members, including the one we're interested in. And then we look at a free body diagram of everything on one side of that cut or the other. All right, so I'm going to go ahead and do that now. Here's this member. And we're going to draw this one here. This one like this, okay? So I've got these members here that I've made the cut through, right? I've made this cut through this member, and I'm looking at everything on the left side of that free body diagram, okay? And I've got this P hanging out here. I have AY, which is P going up here. And I've got this member force that I'm interested in, FEF. What about these other two forces? Because in method of sections, I cut it through three members. What about these other two? Are they there? Well, yeah, they're there. So that's going to be FBE and FBC, right? So I can label them FBE and FBC. And, I can put some dimension lines here. That's 10 feet. And then I still have that vertical dimension line here. That's 8 feet. All right. So what do I do at this point? Well, for this problem, I'm only interested in FEF, okay? Even though FBE and FBC are all there in the free body diagram, I really only need to solve for FEF because that's what I'm interested in, okay? So watch what I can do. I can get slick here, and I can take the sum of the moments about this joint B down here, right? Everybody see this joint B right here. I'm going to take the sum of the moments about that point. Now watch what happens. I'm going to say sum of the moments about B equals 0, okay? And so this reaction AY, which is equal to P, is going to generate a moment about point B, right? So I'm going to have negative P times 10 feet. Let me write that on the next line so it's a little bit more clear. Negative P times 10 feet. And then I'm also going to have FEF times this perpendicular distance, which is 8 feet. And that's also going to be a negative. So minus FEF times 8 feet. And then that's it, equals 0. Now you might be wondering what happened to FBE, FBC, and this particular P. Well, all three of these forces, their lines of action go through the point that I'm taking the moment about. So they're not going to show up in this moment equilibrium equation. That's the beauty in this. This is a quick process if you know what you're looking at. So FEF is going to be equal to, do some rearranging. We say 10 divided by 8 is 1.25. So I get negative 1.25 times P, okay? So what I've done here is I've solved for FEF in terms of P, and it came out negative. What does that negative indicate from our knowledge of statics? Well, that means that that member is in fact in compression. So I could put a little C there, and we had that discussion earlier when we were reviewing the concept of trusses. So am I done? Well, almost. I've done the majority of the work here. Now, like we talked about earlier, we set this equal to that P critical equation, okay? So I'm going to say FEF, I'm going to set that equal to P critical, okay? And so I'm going to say 1.25 P is equal to this P critical equation because we're investigating the buckling force in that member in EF. So I'm going to say that's equal to pi squared E I min over KL quantity squared, okay? And what I'm able to do now is solve for this value of P, which ultimately is what you can hang on both of these joints down here. Because remember, this FEF, where we got it to be 1.25P, that's a result of these two P's hanging at the bottom of this truss. So if I just do a little bit of rearranging here, I'll clearly get P is equal to pi squared E I min over 1.25 KL quantity squared. And then I'm ready to substitute those values in. So let's go ahead and turn the page and do that. So I'm going to say P equals pi squared times 29,000 KSI. And then what was I min before? I'm scrolling back here. That was 0.25 inches to the fourth, okay? So times 0.25 inches to the fourth divided by 1.25 times K, and then L was 10 feet, but we need to convert that to inches because we need to have consistent units, and notice we have inches built in everywhere else, okay? And so I can crank this through, and I'm doing that in my calculator right now, so you can do it along with me. 3.14 pi squared times 29,000 times 0.25 divided by that factor of 1.25, and then also divided by 10 times 12 squared, okay? And so when I crank this through, I get 3.97 kips as P. So I'm going to punch that in one more time. I did not work this out ahead of time, so I'm going to do it one more time, make sure I'm punching in everything correctly. Pi squared times 29,000 KSI times 0.25 inches to the fourth. And then we're going to divide that by 120 inches squared, and we're also going to divide it by 1.25. Yeah, I get 3.97. Really, it's about 3.98. So I can adjust that. 3.98 kips, okay? So we'll make a note here. We can apply P equals 3.98 kips to joints B and C I'll say, let me reword that. We can apply up to P equals 3.98 kips to joints B and C without member EF buckling. Okay, now if you put 3.98 kips on each of those joints, then member EF will be on the verge of buckling. It will just barely start to buckle. So in a real life design situation, you wouldn't want to get that close, okay? In a real life design situation, you would actually, as an engineer, you would say, you build in some kind of factor of safety, and you would say, okay, you can apply maybe 3 kips or 3.5 kips or 2.8 kips. You would not take it barely up to when it's about to buckle. So just keep that in mind for an engineering design situation. But this is the value that will barely just make that member want to buckle. Okay, so that concludes this example. If you found this helpful, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.